Okay, the next talk will be given by Rahul Santhanam, and it's about a new algorithmic approach to uniform lower bounds. Thanks, Rahul.
Thanks, Igor. Yeah, sorry I can't be there in person. I guess COVID is still a thing, but I'm grateful to the organizers for allowing me to give this talk online. Yeah, so I'm going to be talking about an algorithmic approach to uniform lower bounds. And I'm going to start the talk by giving some background and motivation for thinking about uniform lower bounds. And then I'll talk about the specific approach we have in this work and various features of it. Okay, so yeah, so many of the major questions in complexity theory, such as the NP versus P question or the P space versus P question, are about uniform lower bounds. They really ask whether there's a problem in the larger complexity class, NP or P space, that doesn't have uniform Boolean circuits of polynomial size. At least if we expect the standard answer to the question, which is a separation. Since the 1980s, the approaches to these questions have mostly focused on showing non-uniform lower bounds, because that seems like a mathematically nicer question to consider general Boolean circuits and try to argue about them. The attempts have been to show that there's a problem in NP or problem in P space that doesn't have polynomial size Boolean circuits. And that's been sort of approached mostly by considering weaker classes of Boolean circuits and proving low bounds there. So what we're interested in doing in this work is sort of revisiting this uniformity condition and seeing whether we can exploit it better when proving low bounds. We believe it might be significantly easier to show uniform low bounds than to show non-uniform ones, and we're interested in exploring this possibility. Okay, so just to compare uniform versus non-uniform low bounds for NP and P space in terms of what's known, there are, of course, several interesting non-uniform low bounds for NP that have been shown since the 80s. For example, the famous low bound for parity against constant depth circuits, low bounds for majority and mod Q function against constant depth circuits with mod P gates, the low bound for inner product function against depth 2 circuits where the top gate is a threshold gate, an arbitrary threshold gate, and the bottom gates are all majority gates. So these are all sort of like breakthroughs and great achievements in the area. And they all work for relatively simple functions, parity, majority, and inner product. And interestingly, no better uniform low bounds are known, meaning that like there aren't any stronger classes of circuits for which we know uniform low bounds for NP. The reason we know that NP doesn't have uniform AC0 mod P circuits of polynomial size is because it doesn't have non-uniform AC0 mod P circuits of polynomial size. There's no other argument that actually works taking the uniformity condition into account. So that's a situation for NP. And there's some frontier non-uniform low bound questions for NP. And two of these frontier questions is NP in ACC0. So ACC0 is just constant depth circuits with mod M gates, where M is an arbitrary composite. Does NP have depth 2 circuits, threshold gates, so threshold of threshold circuits? And these are both very challenging questions. People have thought a lot about them. Of course, for ACC0, we have Ryan Williams' result, which says that NEXP doesn't have ACC0 circuits of polynomial size, and Marianne Williams showed how to extend that to non-touching quasi-polynomial time. But that seems quite a different kind of result than actually proving a low bound for NP. And so we're still very far from doing that. And the question is, maybe the uniform versions of these questions could be easier to approach. That's what we're interested in exploring. And another reason to look at uniformity is because the well-known natural proofs barrier applies to non-uniform low bounds, but it doesn't seem to say anything directly about uniform low bounds. So perhaps we have more of a chance of showing uniform low bounds. Well, and then if you consider polynomial space, the best known uniform low bounds for polynomial space are the same as for NP. So we don't really know how to do any better if you're trying to prove low bounds for polynomial space than you do for NP when trying to show non-uniform low bounds. And the reason for this is that the known non-uniform low bound techniques typically establish low bounds for very simple functions, such as parity and majority and so on. There's typically some sort of complexity measure that's being analyzed, and you say that the restricted circuit class has a property that functions in that circuit class have small complexity, and then you find some function that requires large complexity, and that function is often a simple function, like majority and a product. So the difference in this case of p-space is we know much better uniform low bounds. So for example, by the space hierarchy theorem, it follows that p-space doesn't have log space uniform Boolean circuits of polylogarithmic depth. Here, log space uniform means that there's a Turing machine which produces the Boolean circuit in logarithmic space. So that's what the uniformity means here. So that's something that follows directly from the space hierarchy theorem because polynomial space is not in polylogarithmic space, but it's wide open how to prove similar non-uniform low bounds. It's wide open even to prove low bounds for log depth circuits or for branching programs. So in this setting, we can ask, we do have by space hierarchy theorem uniform low bounds that are better than non-uniform ones, but we can ask whether we can at least formulate an approach towards even stronger uniform low bounds. Example, the p-space is a speed question. So let me say a little bit about uniformity and what's known about how to exploit it. So exploiting uniformity is typically done via hierarchy theorems, which are some of the few unconditional low bound results we have in complexity theory. Hierarchy theorems for time, space, non terms, and alternation, all of which are shown via diagonalization results, diagonalization methods. Typically involving kind of like if you want to show that there's a language that isn't in a certain resource bound, you kind of like diagonalize against all machines with that resource bound by simulating the machine and doing the opposite, either directly or in a delayed way, as in the hierarchy of long terms of alternation. And there's also indirect diagonalization results, which incorporate diagonalization methods and combine them with other techniques to prove uniform low bounds. So examples here are time-space trade-offs for satisfiability. For example, if you want to show that satisfiability can't be solved simultaneously in time at 1.5 and space logarithmic, then you assume the opposite, and then you kind of use a simulation result for simultaneous time and space bounded complexity classes to contradict a hierarchy theorem. And so that's how the indirect diagonalization works there. And there's also the result of Allender that permanent is not in D-log time uniform TC0. TC0 is constant depth circuits with threshold gates. And D-log time uniform means it's a stronger uniformity condition, which means that you can check if two gates are connected in time proportional to the labels of those gates. So this result of Allender is also proved by assuming the opposite and showing that there are certain complexity collapses as a result, and that this implies a contradiction to a hierarchy theorem. So finally, everything relies on hierarchy theorems and contradicting hierarchy theorems. And I'm just going to give a quick example of such an argument. So this is sort of like a folklore argument that NP isn't a uniform AC0 polynomial size. Of course, we know from the switching lemma and like the famous results of like ITA and first accepts and so on that NP doesn't have non-uniform circuits or constant depth circuits. But here's an argument for uniform circuits. But you assume the opposite, and then you use the fact that uniform AC0 is contained in P. So if NP is in uniform AC0, then we have that NP equals P. And NP equals P implies a collapse of the hierarchy. So we have that for every integer I, that sigma IP equals P, and is contained in this class uniform AC0. And then we use the fact that SAT is NP complete. So by assumption, SAT is in this class uniform AC0. So it has uniform depth k circuits of polynomial size for some fixed integer k. And we don't know which k there is, but there's some such k. And since SAT is actually complete under a very strong notion of reduction under D-log time uniform projections, it actually follows that all of NP has uniform circuits of polynomial size for this depth k. But now we can use sort of like a well-known correspondence between D-log time uniform AC0 and sigma and alternating time. So D-log time uniform AC0 depth k is known to be the same as sigma k time polylog. And by using that, we get that sigma k polynomial time is a sigma k time polylog, which is the contradiction to a hierarchy theorem for alternating time. So this is how the indirect diagonalization works. It eventually contradicts the hierarchy theorem for alternating time. But the crucial aspect of this argument is the connection between alternating time and uniform constant depth circuits, and the fact that there's this correspondence. And in particular, it's unclear how to use this method for any classes that are stronger than AC0. We don't know, for example, how to use such an argument to show that NP is not a uniform AC0 mod P. So one question here is there a way to generalize this low bound technique to apply to stronger uniform circuit classes, AC0 mod P, AC0, and so forth? So that's on the motivation for us. Okay, so let me now say something about what an algorithmic approach to low bounds means. So typically, I mean, as we well know, complexity low bounds are often very hard to show. The reason is that you want to kind of show that some computational task is impossible, and it's not always clear how to go about that. And one sort of intriguing possibility is to reduce the low bound to some algorithmic task to show that there is some algorithmic task which we believe is doable, such that performing that algorithmic task would imply the low bound. I mean, this seems sort of paradoxical at first because the low bound shows that the algorithms don't exist. But in fact, in complexity theory, there are many instances of this phenomenon where there are equivalences between algorithmic results and low bound results. So, for example, complexity theoretic pseudorandom pseudorandom generators are algorithmic objects, but their existence is equivalent to Boolean circuit low bounds for X. This is due to Nissan Vigneson and several works after that. And then, even more close to what we're doing is Williams' algorithmic approach to proving circuit low bounds for next for non-touching exponential time. He showed that if you can find sort of better than brute force search algorithms for satisfiability for a circuit class C, then that implies low bounds for next against that circuit class. And even more impressively, he applied this approach to show that next doesn't have polynomial size ACC0 circuits. The question is, can we hope to do something similar, but for uniform low bounds rather than for non-uniform ones? And that's what we do in this work. We describe an algorithmic approach to proving uniform circuit low bounds for NP and polynomial space. We kind of show various features of the approach that is necessary and the standard complexity theoretic assumptions that can be used to recover various previously known low bounds. And of course, the much more challenging task is to prove new and interesting uniform low bounds using our approach. We make some modest progress here by showing a new low bound for a certain class, which I'll mention at the end of the talk. Okay, so let me kind of tell you what this sort of algorithmic task that we focus on is. So this is a circuit-based sampling task where you're given as input a circuit C from some family, some n variables and of size, say s equals polynomial in n, such that C accepts at least a 2/3 fraction of all inputs. You promise that C accepts most of its inputs. And the task is to sample some element of the set of satisfying assignments of C. Notice that 2/3 of all assignments are satisfying. But you want to output some satisfying assignment with probability significantly better than random guessing, say with probability like n to the 4th times 2 to the minus n, some polynomial times 2 to the minus n. You want to kind of like, give more weight to some specific satisfying assignment rather than others. I mean, of course, there's a trivial algorithm that just outputs a random string of length n that runs in time n, and it outputs each element of the satisfying assignments of C with probability 2 to the minus n. So that's a trivial algorithm. And the question is, can we find an algorithm that's almost as efficient, it's not too much less efficient, but beats random guessing for some element? We don't care which element it is, but for some element, we want to do much better than random guessing. And here's a sort of simple algorithm that works. It's just sort of like you pick, say, polynomially many strings independently and uniformly at random, simulate C on each one, and output the lexicographically first one that satisfies C. So this is going to bias the assignment that's output towards assignments that are sort of lexicographically smaller, and in particular, the lexicographically smaller satisfying assignment is going to be outputted with probability at least n to the 4 over 2 to the n. So it's a very, very simple algorithm. So this is nice, but the issue for us here is the running time, which depends on s. So, and s is an arbitrary polynomial, and we want somehow to use resources which don't depend on s. I mean, of course, that seems unrealistic when you consider running time, because after all, the input is of size s. So how do you run in time less than s? But we could think, for example, of using space that's smaller than s. Notice that this algorithm I've described here also requires space at least s, because you're picking these strings and then you're simulating the circuit. And to simulate the circuit, you need to keep track of the internal values of gates. And so you need space s for this algorithm. But the question is, maybe by kind of like analyzing the circuits in a more sophisticated way, you can come up with an algorithm that runs in smaller space. And if you do, you'll get a low bound from it. That's the main theorem. So we say that a circuit class K has space-efficient non-trivial sampling if there's a randomized algorithm running in some fixed polynomial space that depends only on n, the input length to the circuit, that solves the sampling task that I mentioned. And the important thing here is that this constant c in the space bound doesn't depend on the constant in the size of the circuit that's being analyzed, the polynomial size of the circuit that's being analyzed. And the theorem is that if a circuit class K has space-efficient non-trivial sampling, then P space doesn't have log space uniform K circuits of polynomial size. So here's a fairly natural algorithmic task. Given a circuit and you want to kind of like output some satisfying assignment of the circuit with probably slightly better than random guessing, and do it in sort of non-trivial amount of space, and that implies these low bounds for polynomial space. And as a corollary, for example, you can instantiate K to be inside all Boolean circuits. So circuit here is a class of Boolean circuits. So if you can do space-efficient non-trivial sampling in that case, then you get that P space doesn't equal P, which is sort of an interesting connection. I mean, of course, there aren't that many other interesting examples of circuit classes K where this gives you a meaningful consequence because of the space hierarchy theorems, which means that basically any sort of like class that's within like polylogismic depth, we already have uniform low bounds for. So we're really interested only in getting uniform low bounds for classes that don't have polynomial depth using this approach. So that's one sort of setting in which our approach can be used. But the more interesting setting is for low bounds for NP. And here we need to consider a slightly different sampling task where the input is not this circuit C, but some other circuit that succinctly encodes a circuit C. And this circuit D is from the same class, it's of size n, and succinctly encodes this bigger circuit C. And the task is the same as before. We need to output a satisfying assignment with probability better than random guessing. We define similarly what it means for there to be an efficient non-trivial sort of like sampling for this for circuit class K in the succinct setting. That means it's a randomized algorithm running in polynomial time, which solves sampling task with success probability at least say n to the fourth. N to the fourth is sort of arbitrary here. I suspect that anything with super constant will work, omega 1 over 2 to the n, and solves this task. And the theorem is if that a circuit class has sufficient succinct efficient non-trivial sampling, then NP doesn't have uniform K circuits of polynomial size. And in fact, the conclusion to this theorem, the low bound, holds even if the sampling algorithm is given access to an arbitrary oracle of the polynomial hierarchy. So you can really relax the sampling algorithm's resource constraints and give it access to an arbitrary oracle in the polynomial hierarchy, and the conclusion will still follow. And there's some interesting corollaries from this. So because we require almost no assumptions of the circuit class K, apart from that can be simulated by general Boolean circuits, we don't, for example, require that it has closure properties of any kind. In particular, this is potentially applicable to these frontier questions that I mentioned, to getting uniform ACC low bounds or uniform threshold of threshold low bounds. And I should mention just a couple more maybe interesting features of this connection. And one is that here, in this connection, it's really important that we really using the power of NP. Like for many standard non-uniform low bound techniques, the low bounds you get are for simple functions that are in polynomial time. But of course, such techniques can't hope to eventually give you super polynomial circuit low bounds. I mean, that would be contradictory. But this connection actually takes advantage of the power of NP, and the connection for P space takes advantage of the power of P space. And it's also fairly generic. It works for any circuit class K. Um, so uh, yeah, so it has and it really also exploits uniformity. We don't know how to make this approach work for non-uniform classes. There might be some other algorithmic approach to non-uniform low bounds, but we don't know of one. Okay, and I'll say something very quickly about the proof. How much time do I have, Igor?
Can you hear me?
Yeah, yeah.
Yeah, so 10 minutes in total. Maybe like if you could finish in like 7 minutes so we have time for questions.
Okay, great. Just to say something very kind of briefly about the proof. This is just a very high level sketch. So the proof crucially uses resource bounded congruent complexity. And in particular, it uses a notion of probabilistic time bounded congruent complexity that was introduced recently by Goldberg cabinets, Liu and Oliveira. And like what we do is we consider the set of strings of almost maximal probabilistic time-bound congruent complexity. So like some set of random strings. And we argue that if the uniform low bound we want doesn't hold, then the set has small uniform circuits. And then by running the sampling algorithm on these small uniform circuits, we obtain some satisfying assignment of for these circuits with probability much better than random guessing. And it turns out that if you can output such a satisfying assignment probability much better than random guessing, then it means that the satisfying assignment Y has resource bounded congruent complexity much less than N. But then Y is supposed to be a satisfying assignment of Cn, and Cn only accepts strings of high complexity, so that's a contradiction. So Y has complexity much less than N, but Cn only accepts strings of congruent complexity close to N. So that's a contradiction. So it's an argument by contradiction, but it works in quite a different way to most uniform low bound results, which rely on hierarchy theorems. It doesn't go through the standard hierarchy theorems. And that's part of why we're able to get such a generic result. So you might ask, well, okay, so here's a connection. Here's an algorithmic task. This algorithmic task, if you can solve it, that implies these low bounds. I mean, the low bounds look impressive, but the algorithmic task looks extremely hard, and why should we even believe that it's possible to solve it? Well, for one thing, at least in the world we believe we live in, these algorithmic tasks are solvable because they follow from standard cryptographic assumptions. If one-way functions exist, then like the strongest version of these sampling tasks is still solvable. And the reason for that is that one-way functions imply that there's pseudorandom generators, cryptographic pseudorandom generators with small seed length. And just by outputting, sampling a random output of cryptographic pseudorandom generator, you can solve the sampling task. So that's a straightforward way to do it if one-way functions exist. So that's okay, but it also turns out that something more interesting is the case that under like very believable and relatively mild complexity assumptions that there's actually an equivalence between uniform low bounds and certain versions of our algorithmic tasks. So if you assume that exponential time requires exponentialized Boolean circuits, so this is of course a very difficult question, but it's sort of like morally different, perhaps easier than the question of proving like NP in order to P or P space in order to P. Then under this assumption, it turns out that there's an equivalence between P space not equal to P and a version of our algorithmic task. So not just does our sampling task imply low bounds, but it's implied by low bounds under de-randomization assumptions. And can also use kind of like our approach to give sort of like a new proofs of various known uniform low bounds, so the space hierarchy theorem and a Wallender's low bound for the permanent. So these are different proofs that, as in the proof template, don't rely on hierarchy theorems, but instead use a different kind of diagonalization based on resource bounded common graph complexity. And then we are also able to get a new low bound that wasn't known before, and this is for the class AC0 of threshold. So constant depth circuits with a bottom layer of threshold gates, of arbitrary threshold gates. It's unknown, it's an open question whether NP or even P space have polynomial size circuits for this class. So this is a low bound that we don't know how to show. We know it for NX using Williams' algorithmic method, but we don't know it for NP or P space. But for the uniform version of this class, we can get a low bound, so we can show that NP doesn't have the log time uniform AC0 threshold circuits of polynomial size. So I guess that's in the direction that I mentioned earlier. So I gave the argument that NP isn't a uniform AC0, and I asked whether this can be extended to more powerful circuit classes, and this is one example of how to do that. So it turns out that while this is a new result, we proved using our approach, it turns out it can also be recovered using like more standard indirect diagonalization approaches. Sorry, and just to finish, as sort of like a takeaway, or to give some perspective, I'll maybe just mention this sort of this perspective of sampling versus simulation for uniform classes, and what these new connections might sort of like add to understanding. So almost all previous proofs of uniform low bounds against circuit class K ultimately rely on diagonalization and hierarchy theorems, which work by simulating and doing the opposite. And in contrast, the connections that we present only require efficient sampling of a distribution close to the output distribution of a circuit from the circuit class K. This is potentially a much weaker requirement, because if you can simulate a circuit from K, that allows us to solve a sampling task, but the other direction doesn't hold. It might be that sampling it can be done much more efficiently than simulation. And among other things, this motivates further investigation of the complexity of sampling distributions. So this is the direction that Emanuele Viola and others have initiated, and there's some work on it, but not very much. And so perhaps there might be some connections between that line of work and these connections. And also, I guess these sampling tasks that are being presented here are sort of like new. I mean, so it might be interesting to study even like very special variants of them and see what can be done, just to understand them and in terms of like a new perspective on algorithms, not just from the motivation of proving new low bounds. I think that's all I have to say. Thanks.
So questions for Rahul?
Sorry to have not very interesting question, but what is CKT? It's mentioned.
Rahul, I don't know if you could hear the question.
No, I can't hear anything except what you.
Sorry, I think it's about the notation. What is the meaning of CKT in your slides?
Oh, CKT is just a class of Boolean circuits. When we talk about these sampling tasks, we talk about them for some family of circuits. So we could talk about them for like constant depth circuits or formulas or general Boolean circuits. So CKT just refers to the class of general Boolean circuits. So that means that we are able to solve the sampling task for any circuit whatsoever of bounded finite.
Any other question?
Just a slight comment, not a question. So Kolmogorov himself suggested that if you want to show P not equal to NP, then you better not focus on NP complete equivalence, but focus on something like time-bounded Kolmogorov complexity. This paper indeed proves lower bounds for PKT.
Yeah, so
indeed it's related.
Hanling has a question which essentially translates to this seems to be a good direction to prove lower bounds based on Kolmogorov's comment that we shouldn't focus on NP-complete problems, but instead on less structured problems. I hope I...
Yes. Yes, yeah, but I mean, it might turn out these problems are NP-complete anyway. But yeah, but yes, yeah, but it's a different approach than focusing on SAT, the sort of ones. Yeah, I mean, I guess there haven't, like, most approaches have actually focused on very, very structured problems. I guess there's the very unstructured problems such as SAT, where, I mean, there we have time-space trade-offs, but we don't have many other low-bound techniques that exploit the unstructuredness of SAT. But I guess Kolmogorov complexity is somewhere in the middle, and I think that's what Kolmogorov meant. It's sort of like in between, and might be the right place to look for low bounds.
Okay, let's thank Rahul again. And thanks for joining us online, Rahul.
Yeah,
See you.
thanks. Bye.